Okay, section 9.2 starts out where we really start going through the full process of going through a significance test where we're going to test a claim that's been made about a population proportion. And if you recall, as we've been working through these various proportion problems, actually since chapter 7, we've been, when we did the sampling distributions for proportions, we had kind of 3 different conditions that we had to check. And so these should sound familiar at this point. 1, making sure that the data came from a well-designed random sample. 2, that it's independent, the observations are independent, and that basically relies on that 10% condition, that we make sure that if we're doing this without replacement, that we're not surveying more than 10% rather of the population. And finally, and this one's important, the large counts condition allows us to use those z-scores and things like that. Please keep in mind the central limit theorem, that has to do with sample means, okay, not proportions. So when we're doing the large counts condition, what we're technically checking here is that the number in our sample times the number of successes as well as the number of failures will always be greater than 10. Okay, take note that you'll notice there's a little p sub 0 that's used here. What you're going to use for the p-value is you're basically, since we always do these significance tests under the assumption that the null hypothesis is true, whatever value is specified by the null hypothesis as being the claimed proportion, that's what you're going to use for the p in this large counts condition. Okay, so whenever we run these significance tests, we have mentioned before in the last section that we're collecting a sample and then we're going to kind of assess the strength of the evidence that's revealed by that sample against the null hypothesis to once again just kind of conclude whether we're going to reject the null hypothesis or fail to reject. And what we're going to be doing here when we go through this is we're going to be calculating a test statistic with some of the values that we have. And that test statistic is nothing more than it's going to give us a z-score. Okay, and with that z-score, we're going to be able to calculate the p-value. Okay, and if you recall the p-value in section 9.1, that was representing the probability of getting a sample proportion as extreme or more extreme than the one that we got. Okay, and when we start to compare that p-value against the alpha significance level, if the p-value is less than the alpha level, that's when we reject the null hypothesis. Okay? So to get this test statistic, this right here should look familiar. This is just kind of a very generic form of how we get our z-scores. We always take our statistic minus the parameter, and then we divide that by the standard deviation. Okay, now I'm going to change this slide over. This is not on your notes page that you have before you, but this is on that green cardstock that I had given you earlier in the year. And what I want to draw your attention to is the fact that on this green cardstock, because this is really the formula sheet that you're going to be given, you can see generically there's that formula for a standardized test statistic, which is really just a z-score. Okay, and just like the confidence intervals, how it's just kind of written generically, this is what you're going to use here when we're doing these significance tests. And so what you're going to need to do for the sample proportion significance test is you're going to take the standard deviation for your sample proportion, and that's going to get plugged in to the denominator portion here for your test statistic. Okay, so I just want to reference that so you understand that this right here is technically on the formula sheet, okay, that you're given. Okay, that's on the formula sheet. Okay. So what we're going to do when we use that formula is we're really using that formula, but we're going to be making these substitutions in it. Okay, we know that the test statistic is what we got from our sample proportion. Okay, so that's going to be the sample proportion. Okay, the parameter, that comes from the null hypothesis. That's kind of the claimed proportion. Okay, and then lastly, and once again that you saw on that other slide there, this part right here, which is the standard deviation of the test statistic, that formula is actually on the formula sheet. Okay, so this is what you're going to plug in to get your z-scores. Okay, now when you have your alternative hypothesis, okay, those can be one-tailed or two-tailed. Okay, and the area that's associated with that test statistic, it depends on which direction that alternative hypothesis goes in. Okay, so if it's a less than, okay, if it's a less than, okay, like this one right here, that means your p-value is everything to the left. So that would be this middle graph right here, okay, where right here's the z-score, and then the probability of getting anything at that z-score or more extreme, so in that case to the left, that would represent the p-value. Okay, as opposed to if your alternative hypothesis is greater than, that would be this picture here, actually right here where the z-score is, and that would be everything to the right. And then lastly, finally, if it's a does not equal to, that's when you have two-tailed. Okay, and this is really important right here. That means the area that's in the tail, it actually gets doubled. Okay, it gets doubled there. So when we do these significance tests, just like with the confidence intervals, we kind of had like a process, state, plan, do, conclude. Well, with significance tests, they have this little mnemonic kind of acronym here to help you remember the process of these steps. And so I'm just going to run through this with you, but it's the word phantoms. And this helps just kind of list all the things that often the rubrics are looking for, if you remember this word phantoms. Okay. Now, much of this we've actually discussed in section 9.1 when we were kind of introing significance tests. So what you're going to do to start this out is you're going to always list the parameter that the claim is about, and then you're also, the H is you're going to list the null hypothesis, the alternative hypothesis, and then you're going to list whatever the alpha level is. So the P and the H kind of represent like the state portion of the state, plan, do, conclude. Okay. Then we have the A, which they're letting the A represent assumptions, which is what we've previously called conditions. So you would list your 3 conditions for the proportions, and then you would also name the test. Okay, this is what makes up the plan. By the way, the name of the test, you could see it written a couple different ways, but I always prefer to name it the way that it looks on the calculator. On the calculator, it's a 1 proportion, Z, but instead of interval, for confidence interval, it's a test for significance test. Okay, 1 prop Z test is how it'll look on the calculator. Okay, now these are the 2 parts here that we have not done yet. We haven't learned how to get the test statistic. Okay, and the other thing we're going to be doing is we're going to be drawing the curve, okay, as part of that test statistic. That's the z-score, and then we're also going to get a p-value. Okay, that's the do step. Okay, and then this last part, we actually have practiced this quite a bit in the last section. The conclude is where we make a decision, and that's where our decision is either going to be to reject the null hypothesis, or it's going to be to fail to reject the null hypothesis. And then we draft a conclusion in context, saying whether we have convincing evidence in favor of the alternative or not convincing evidence. And so I just want to run through an example that actually is already all done for us so that you can just kind of see all the different parts and pieces. This is just talking about the show American Idol, and there are 12 contestants. And the contestants, it says here, often wonder if there's really an advantage to performing last. So to investigate, it says researchers selected, this is important, a random sample of 600 college students, and they showed each student the audition video of 12 different singers. Now, for each student, the videos were shown in a random order, so we would expect, if there really is no advantage whatsoever to performing last, we would expect approximately 1/12 of the students to prefer the very last singer that they view. Okay, that's assuming that the order doesn't matter. And I'll tell you, your null hypothesis is often a statement, well, it's always the statement of equality, but that often means that that's when you're saying, look, there's no difference. It doesn't matter. The true proportion of students who are going to prefer the last singer, if there were 12 singers, is going to be 1/12. Okay, and then the alternative usually goes against that idea. Okay, so it says here in this study, 59 of the 600 students preferred the last singer. Okay, so what that means is the sample proportion, 59 out of 600. Okay, and I think as a decimal, maybe that would round to almost about 0.10. Okay, so we want to see, do the data provide convincing evidence? This is normally how things are worded when they're wanting you to run a significance test and they're giving you the significance level of 5%. So you can see as we go through the PHANTOM acronym, the P, we're just listing what the proportion, the true proportion of students who prefer the last singer. Okay, on the H, we're listing, and here we're saying, well, maybe there actually is an advantage to going last. That's why we chose greater than 1/12. Okay, we always list the alpha level there. Okay, and then you can just see as we go down through, we're checking off kind of our list of conditions, and we've done those a bunch of times. We don't need to talk about that. Okay, here they wrote this. I prefer to name the test a one-prop z-test myself, but the other name could be a one-sample z-test. Okay. They also accept you writing the generic formula. I don't know why you'd write that, but okay. And then you can see here for the T, this is us obtaining the Z value, okay, the Z score, which is that test statistic. In this example, we just used kind of the fraction 59/600. You could use these as a decimal, but you can see this was the sample proportion. This was the proportion from the null hypothesis, and that was that standard deviation of the test statistic. Okay, so I don't have on here a curve, which I should have drawn. Okay, down the middle would be what we're assuming the true proportion that would prefer the last singer. That's 1/12. Okay, and then I would say my 1.33, we'll say that's about like right here. This is my z-score 1.33. Okay, which would represent my sample proportion of 59/600, okay, and the alternative was everything greater, and so this is what I'm looking for, getting that area right there. Okay, so the p-value, okay, represents the probability of getting a sample proportion of this value or greater. Okay, so we've done this a bunch of times too. Okay, I've got my z-score of 1.33, so I'm going to do lower, upper. I might do 10,000 here for that. Okay, I'm going to do 0 for the mean and 1 for the standard deviation, and I get a p-value of 0.0918. So the M is make a decision. This is where I compare, since the p-value of 0.0918 is greater than the alpha level of 0.05, our decision is to fail to reject the null hypothesis. We say there is not convincing evidence. And remember, then the rest of this is all talking about the alternative, that the true proportion of students who prefer the final singer is greater than 1/12. Okay? That means there's not really an advantage to performing last. Not convincing evidence, anyhow, saying that. Okay? All right, so we're going to go through one example here so we can kind of go through one just sort of from start to finish and make sure that you're all right with this.